All right, so a little bit more on inductors here. We talked about parallel plate capacitance when we talked about capacitors. Now we're going to talk about wire wound inductance. Basically, what parameters set the inductance, which is how much, basically talks about the same way that for a capacitor, we talked about how capacitance told us how much charge the capacitor could store, which is directly related to the amount of energy that it could store. The inductance tells us basically how much or how capable this inductor is of storing energy in the form of a magnetic field. Okay, so more inductance means that it can store more energy quite directly. They're proportional to one another. And so we'll look at these one by one. The first one says that inductance. Okay, so let me actually just go ahead real quick and just talk about how inductance is measured. It is measured in henries. That's the unit H. And the symbol for an inductor is L. It's not I because I is already used for current. So I actually am not sure where the L comes from. Probably should know that, but I don't. And so the way that capacitors and capacitances use C, inductors use L, and the way that capacitors are measured in farads, inductance is measured in henries, okay? And similarly to how I talked about how capacitors are typically in the microfarad and nanofarad range, we typically see inductors in the millihenry and microhenry, even down to the nanohenry range. Again, a henry is a very large unit. You won't see a 1 or a 2 henry inductor most likely in circuits. You'll usually see millihenries, microhenries, and even down to as small as nanohenries, okay? So now let's get into these bullet points one by one. Pull out my highlighter. Inductance increases with the permeability of the core. Now what the heck does that mean? Well, that's this mu. This mu here is the permeability of my core. So this material in the middle is the magnetic core, and permeability is basically a measure of how well this material can store a magnetic field or store energy in the form of a magnetic field by polarizing its magnetic dipoles inside the material. So a better magnetic material that is more capable of magnetically polarizing will result in a inductor that can store more energy in the form of a magnetic field, okay? And so that's the first thing. The second thing is the cross-sectional area of the coil. So if these coils are larger, the actual physical cross-section, then the inductance will increase. They are proportional to one another by this equation. Thirdly, we can see that the inductance increases with the number of turns, and it actually increases quadratically. So if I were to count these turns, there'd be roughly 1, 2, 3, 4, 5 turns in this inductor. So N here would be 5 for this inductor that we're looking at here. And so if we wanted to increase the inductance, then we would increase the number of turns. Lastly, the inductance decreases. The inductance decreases with the total coil length, and so that's this length. And the reason why it decreases with the total coil length is more or less because more length means that we have more space between coils, and more space between coils means that they are not as tightly magnetically coupled, and so you lose some of the ability to store energy in the form of a magnetic field as you space out these coils, okay? So if you wanted to maximize the amount of inductance that you could get out of a coil with 5 turns, you'd want to smash these coils as close together as you could, okay? So that'll wrap up my video on wire wound inductors, and in the next video I'm going to talk about the IV relationship for inductors, or the current voltage relationship for inductors.